Okay, to start respiratory physiology, you don't necessarily need to know the gas laws per se by name, but you do need to know um, basically the properties that they explain and what's going on. You should understand that volume and pressure of a gas are inversely related at any given temperature, assuming temperature stays the same. When the volume of a gas increases, the pressure on that gas decreases. When a volume of gas decreases, the pressure increases. That's for your inverse relationship. When one goes up, the other goes down. Gases also move down their own pressure gradient, depending on the uh, the amount of the ratio that they are of the whole of the total gas mix, independent of each other. So oxygen and carbon dioxide will move down their own respective pressure gradients independently of each other and in opposite directions. Um, Different gases will dissolve in fluids differently. Carbon dioxide is much more soluble in liquids than oxygen, so carbon dioxide diffuses much more rapidly than oxygen. And if you notice, the partial pressure differences to actually move a certain amount of carbon dioxide are much lower than the partial pressure differences than oxygen experiences as well. So again, just I wouldn't ask you to know by name, but know, the laws and how they work, basically. Okay, so um, using a little diagram of the lungs, you see here, you've got basically your thorax. They're showing you the trachea, basically through that black stopper. They're pulling the white thing, which represents the diaphragm, and being that the thorax is sealed and there is no place for air to enter. When you move the diaphragm, it in respect then moves the lungs. So when you pull the diaphragm, assuming there's no structure, no pneumothorax, which would be air within the thorax, a movement of the diaphragm will have an effect on the lungs and will cause movement of the lungs. Okay, so when you look at what's going on during inspiration and expiration, so you start off this slide on the left at end of expiration, so it just expired. Um, so for inspiration, to take a breath in, our diaphragm contracts, and in doing so, increases the volume of our thoracic cavity. So if the volume of the thoracic cavity is increased, again, remember volume and pressure are inversely related. So if the volume increases, the pressure decreases. So the pressure within the lungs decreases, becomes less than the ambient pressure around us. So air moves down its pressure gradient from outside the trachea into the lungs, down from higher pressure to lower pressure. And at end of inspiration, again at the end of inspiration and expiration, there's no net movement because the pressures have become equal. But at the end of inspiration, the diaphragm relaxes, and through elastic recoil, the lungs reduce in volume. And again, the inverse relationship between volume and pressure. If the volume decreases, the pressure increases. And so the pressure in the lungs increases to above ambient air pressure. So air then moves from the lungs out the trachea. So when we breathe into a spirometer, we get a trace called a spirograph, and that is what you're looking at here. So basically with the spirograph, it gives us the volume. We can measure the volume of how much air we breathe in and out with just an at-rest breath, which is our tidal volume. We can measure the maximum inspiration, the maximum amount of air that we can inhale after a normal inhalation, after a normal tidal volume inhalation at rest. And that is called our inspiratory reserve volume. The amount we exhale after a normal breath is the expiratory reserve volume. And if you notice, the expiratory reserve is much less than the inspiratory reserve. Again, showing that even after we inspire, the amount needed, we have enough elasticity within our lungs to make them much larger and inspire a much larger volume of air. Maximum expiration, the expiratory reserve volume comes from simply kind of closing the chest down and reducing the size of the chest as much as possible. The residual volume is the air within the trachea, bronchi, and bronchioles that can never be really removed. They are, three-dimensional structures with a certain amount of volume, and so the residual volume, that amount of air, will never really be displaced from the lungs. So that just kind of stale, stagnant air mixes with the air that we inhale with each breath. As well, on this slide, you want to know the volumes, to be able to label them on this slide, as well as know the definitions of the volumes. According to page 303 in your laboratory manual. Remember, volumes are directly measured. Capacities, as you see there on the right, are combinations of two or more volumes. The inspiratory capacity is a combination of the inspiratory reserve volume and the tidal volume. Functional residual capacity, again, combination of the expiratory reserve volume and residual volume. Vital capacity is your expiratory and inspiratory reserves plus the tidal volume. And then total lung capacity is basically your vital capacity plus the residual volume. So know what volumes are combinations, or what capacities are combinations of what respective volumes. And again, just another different type of spirograph, but you should again know the capacities and the volumes, both by definition as well as be able to recognize them as on a spirograph, as you see here. So looking at movement of gases during inspiration, we bring inspired air into our lungs with a PO2 of 160. Again, mixes with that kind of stagnant air, our residual volume that never really leaves our lungs. By the time it gets into the alveolus, the PO2 is reduced down to 104, but that is well above the PO2 of the incoming venous blood. The PO2 of the incoming blood is only 40. So oxygen diffuses down its pressure gradient, not concentration, but pressure gradient from the alveolar air into the venous capillaries. Eventually, the oxygen will equilibrate and reach an equilibrium, so that the pulmonary capillaries leave with a partial pressure of oxygen of 104. And at that same time, the partial pressure of CO2 is 45 in the pulmonary capillaries, and it is only 40 within the inspired air. So carbon dioxide travels down its pressure gradient from the blood in the capillaries into the pulmonary air to be expired with the next expiration. So as you leave the the pulmonary capillaries, you have a partial pressure of 104 for the oxygen and a partial pressure of CO2 of 40. Now, the partial pressure of oxygen reduces slightly, if you see, between step 2 and step 3, due to the mixing of deoxygenated blood from the veins, from the bronchial arteries and veins that we mentioned in the slide before. Remember, the bronchioles have their own arteries, veins, nerves, and those veins actually mix with the pulmonary veins before they enter the heart as they leave the lungs. So you actually start your systemic circuit with a PO2 of 95. instead of the 104 from the inspired air because of that. So coming into your systemic circuit, your partial pressure of oxygen within the systemic tissues is only 40. Within the cells themselves, it is only 20. So there's the PO2 is being used by the cell. So it should make sense that oxygen is being used by the cell. It's kind of an oxygen sink, so oxygen is always going to diffuse into that area where there's less oxygen, which is in the cell. Again, the incoming PO2 is 95, so the oxygen diffuses from the blood into the interstitial fluid and eventually into the cell within the systemic capillaries. Oxygen within the cell is 46 partial pressure, and again, incoming oxygen in that arterial blood is only a PCO2 of 40. So carbon dioxide is going to diffuse down its concentration gradient from the cell into the blood. And again, by the time we reach the venous end of those capillaries, the gases have reached an equilibrium. So you have a PO2 of 40 within the blood leaving the capillaries, same as it is within the interstitial fluid, and a PCO2 of 45, again, the same as it is within the interstitial fluid. So those are the amounts of gas, PO2 of 40 and a PCO2 of 45, that if you went back to the prior slide, you would notice that you start your pulmonary circuit again with that amount of gas. Just like everything else, oxygen diffuses down its pressure gradient from where it is in most highest quantity to where it is in lowest quantity. So again, how gases actually travel. You should know the relative amounts and kind of the transport methods of both carbon dioxide and oxygen. Very little carbon dioxide is actually dissolved within the fluids, but some is. 23% is actually bound to hemoglobin, just as oxygen would bind to hemoglobin. But the majority of carbon dioxide, 70%, is transported as this bicarbonate and carbonic acid mechanism, where you have carbon dioxide combining with water in the presence of carbonic anhydrase catalyst, becoming bicarbonate, and then carbonic acid, and releasing hydrogen, and that hydrogen then assists oxygen in hemoglobin in releasing oxygen. We're going to see that change in pH will actually change the affinity between oxygen and hemoglobin. So it should make sense. In the same place where you pick up lots of carbon dioxide, that is the same place where you want to drop off a lot of oxygen. So by and large, the majority of oxygen, as you see there, is transported by being bound to hemoglobin, and very little, only 1.5%, is actually dissolved within the gases. And again, this is what you see in respiring tissue. The red cell is picking up carbon dioxide and dropping off a fair amount of oxygen. So you see the exact opposite occurring within the alveoli. The oxygen within the inspired air is diffusing across the respiratory membrane and binding with hemoglobin to become oxyhemoglobin, which is, again, kind of releasing that proton to recombine back with bicarbonate to become carbonic acid, and eventually carbon dioxide and water. That carbon dioxide will diffuse back across the respiratory membrane into the alveolar air to be expired. And as well, the binding of oxygen to hemoglobin also reduces the affinity of hemoglobin to carbon dioxide, and the carbon dioxide is released from the hemoglobin, so it again that small 23% can be diffused across the respiratory membrane as well. And again, that 7% that is dissolved within the fluids diffuses in the opposite direction as well, from the capillary blood into the alveolar air. So it's basically the same reactions that you saw before, just in opposing directions. So you should understand the oxygen hemoglobin dissociation curve. I put this in here because I thought it was important to have a little more visual data and a little more practice in reading visual data and understanding what it shows us. So understand your x and y axis. Your x-axis is at the bottom as your horizontal axis, which is the partial pressure of oxygen in millimeters of mercury. The y-axis is the percent oxygen saturation of hemoglobin. Remember, each hemoglobin has 4 heme molecules, each heme molecule combined to 1 oxygen. So an individual hemoglobin molecule can be either 0% saturated with no oxygen bound, 25% saturated with one of the 4 hemes bound to oxygen, 50% saturated with 2 of the 4 hemes bound to oxygen, 75% saturated with 3 of the 4 hemes bound to oxygen, and 100% saturated with all 4 heme molecules bound to oxygen. Now that's just one heme molecule. Extrapolate that out across millions of heme molecules within a red blood cell, and again millions of red blood cells within a specific volume of blood. So you don't always get 0, 25, 50, 75% increments, but you do very rarely ever get 100% oxygen saturation. The best usually you hope for clinically that you usually see is 98 to 99% saturation. So when you look at this graph, you look at the bottom right, the PO2 in lungs. We can just start off in the lungs. The PO2 in the lungs is about 104, as we saw in the few slides back. Within the alveolar air that we inhale. So at 104, you follow that dashed line up, and you at that curve at 100 PO2 of 104, we are about 98% saturated. 98% of all the hemoglobin molecules within of all of our blood are bound with oxygen. So that blood leaves the lungs and travels into the tissues, and then we will travel into a tissue with a PO2 of 40 in the tissues. And that's tissues at rest, still metabolically active, but not as active as they could be. So if you follow that dashed line above the 40 at a PO2 of 40, we are about 75% saturated. All right, so 75% of all of our hemoglobin molecules are bound to oxygen as we leave that tissue. So what that's saying is between the lungs and leaving that tissue, we have dropped off 23% of our oxygen. If you look at the 2 dashed lines on the horizontal, we started off leaving the lungs with 98% of our hemoglobin molecules bound with oxygen, and we left our systemic tissues with 75% of our hemoglobin molecules still bound with oxygen. So we dropped off what was required, 23%, and we leave with what is still a fair amount of oxygen. So we have a fairly good buffer in case we ever needed to drop off more oxygen. So same situation, let's take that at exercise now. So again, you look at your PO2 in the lungs, you leave your lungs with the PO2 in the lungs is 104, so you leave that area with 98% of your hemoglobin saturated. And let's say you get to a tissue at rest, and the PO2 in that tissue looks like 15. So your PO2 in that tissue is very, very low. Well, if you look at the curve, it is very steep in that region, that region of PO2 and along our x-axis. So what that means is, and we get a change of PO2 from 40 to 15, we don't just drop off 23%. Now we are only about 25% saturated, so we have dropped off 73% of the 99% of oxygen that we were carrying. So now, since we are under exercise, we leave those systemic tissues with less oxygen. We now leave 25% saturated instead of 75% saturated. So we've dropped off an extra 50% of the oxygen that we were carrying when you go from tissue at rest to tissue under exercise. So the other thing you just kind of see on this graph is the difference in slope and steepness. So if you look at the PO2 in the lungs, look at the graph between about 75 and 100. It's fairly flat. Okay, it's not very steep in that region. A change a change in PO2 does not really it doesn't really change that much of the O2 saturation. So when you look at the kind of the more the left part of the graph, the steeper area between, let's say a PO2 of 40 and 0, from that area the graph is very steep. So you have a relatively small change in your x-axis, a small change in PO2, that leads to a large change in the O2 saturation. So a small change on your x-axis leads to a large change on the y-axis, and that is a product of the steepness of that slope or the steepness of that curve. So the curve has different shapes and different regions that serve different functions. So we have because this is very steep, we have a large response to a relatively small change. So that curve will also shift as well based on the varying conditions. So you need to understand what will cause the curve to shift to the left versus the right. So if you look at the first graph on the left there, graph A, in this tissue, the oxygen hemoglobin dissociation curve has shifted to the right. It has gone from the red curve to the blue curve, and that is a response to a decrease in pH or an increase in CO2, which remember CO2 equals acid. Anywhere you see carbon dioxide, it will tend to decrease the pH of that region, and an increasing temperature. So a shift to the right is what you see in the tissues of the body. Okay, so a shift in the right is also beneficial because it causes to actually drop off more oxygen. So if you notice the dashed line above a PO2 of 15, you follow that up to the red line, and initially without the shift, we would walk out of there with about slightly over 30% oxygen saturation. But with that shift, now you follow that dashed line up to the blue and follow that over. Now we're walking out with only about a 19% O2 saturation. So we've gone from about slightly over 30% to slightly under 20. So we've dropped off a fair amount more oxygen just simply due to the shift in this curve. And again, that shift is beneficial in this region. So it's always beneficial to drop more oxygen off in the tissues. So we see these shifts in the curve will actually benefit us. So if you look at the curve on the right, curve B, in the lungs, the oxygen hemoglobin dissociation curve shifts to the left. So we're going from the blue to the red. So in the lungs, what that actually causes is us to pick up a small amount more of oxygen. So because of that shift in the curve, and again, this shift left is due to increasing pH, decreasing levels of CO2, and decreasing temperature, which again are conditions that you found more in the lungs. The lungs are definitely cooler than the core of the body, and carbon dioxide is diffusing out of the lungs, so there's less carbon dioxide within our lungs than there is within the respiring tissues. Likewise, the CO2, the pH reflects that as well. So this left shift actually allows this to pick up a little bit more oxygen in the lungs than we would have without the shift in the curve. This is just another oxygen hemoglobin dissociation curve from a different textbook. Again, it goes all the way to 100% saturation, so there are some variations that you'll see out there. But I will tell you clinically, you will very rarely see 100% sats. Usually it's 98 to 99 is the best you can hope for. But they do show you the PO2 levels in the alveoli and the systemic tissues that you see along the x-axis on the bottom there. So you walk out of the alveoli with 100% saturation. saturation, and you, again, at rest with a PO2 of only 40, you will drop off 22%, and you'll walk out of your systemic tissues with slightly under 80, with 78% saturation. So, what that's showing you is with um, at rest, you still have a fair amount of oxygen to drop off to tissues that are under exercise. So you've always got that oxygen reserve. These two curves show the isolated effects of increasing temperature and decreasing pH on the oxygen hemoglobin dissociation curve. Again, increasing temperature shifts that curve to the right, and decreasing pH shifts that curve to the right. Both conditions that you would find in systemic tissues, and both conditions that would actually cause for a release of more oxygen within that tissue. It would actually decrease the O2 sats of the red blood cells, and hence when you decrease the O2 sats, where has that oxygen gone? It's been dropped off into the tissues, so that both those benefit or facilitate release of oxygen within the tissues. So just know some of these respiratory diseases. I will give you definitions pretty much verbatim that you see here, and be able to just give me the definition of the respiratory disorder. Emphysema, very interesting one, because it is really when you combine it with bronchitis, then you get COPD. Emphysema is one that, again, also causes people to have to work to exhale as well as inhale. So your elastic recoil is gone. So it definitely also highlights the importance of that elastic recoil in exhalation as well. So again, just know these for the practical as well. And as with the first slide, just know the definitions of the respiratory diseases. I will ask you the definition, and you can just give me the name of the disease. Most likely it'll be a multiple choice type format, something along those lines.